this problem, a number n would be given, and this would be the size of the string. And based on this, we have to construct the string of size n, and this string should be constructed only from the characters a, e, I, o, u. And then we have to give the count of how many strings can be created of size n, of size equal to n. How many such strings can be created? So like for example, for n equal to 1, if I have to create the strings of size equal to 1 using characters a, e, I, o, and u, then clearly each of these would be a string in itself. So the number of such strings would be equal to 5. Then if I have to create the string of size 2, then these are some of the examples like e, I, and so on. But there's a constraint that has been given, that is that all the characters should be in a lexicographically sorted order. So what I mean by this is that e can only be followed by e, I, o, and u. It cannot have an a cannot be there. Now if I were to solve this problem in a like if suppose the problem would have been like I just have to give the count of all the strings of size n, given size n, without any constraint, then answer would simply have been 5 to the power n. Why? Because there would have been n places, and each of these n places would have 5 choices each, so the answer would have been 5 to the power n. But in this case, we will have to use a bit of recurrence relation. Now before we get into recurrence relation, let's first understand the concept of state. So how I define state over here is that if suppose I have a string of size n minus 2, this is one state. Then then I need to append some characters. I need to append some characters in order to arrive at another state, and this state would determine the new size of the string to be just greater than the previous one by just one character, right? So if I have to increase the size by one character, then I have to take a previous state, append some characters to it, then I'll get the next state. And similarly, if I have to construct a string of size n, then I need to take the string of size n minus 1, this previous state, do some appending operations to it, and then I'll get the string of size n. So if I have to say, for example, then if I try to denote this, I can denote in this format, n minus 2a. What I mean by this is string of size n minus 2, ending in character a, and I'm actually trying to denote count for such strings. So this is nothing but this. So this function gives me count of such strings that satisfy the above criteria, that their size is equal to n minus 2 and last character is a, and this is the size. So then if suppose I have to so this notation is clear. So now if suppose I have to talk about all the strings that end in a, then what I can do is, if suppose n minus 2 is the size for the strings that end in a, if I simply append an a to it, I will get the string of size n minus 1 ending in character a. So what can I say about the count? The count of this is equal to the count of this, because the rule is that I cannot append. Now always all the characters before a have to be lexicographically smaller than a, right? So they can or equal to a, so they would all be a's, right? So since they are all a's, if I append an a, I would get the next answer. Simply I would be appending an a to it and I would get the next answer, because I cannot append any other thing. A can only have a's before it, right? So this is the rule that we have for a single character a. But if suppose I want to apply this for e, what I can do is n minus 2 e, f of n minus 2 e will be equal to f of n minus 1, n minus 1 e would be equal to n minus 2 e plus f of n minus 2 a. What this means is, if I have a string of size n minus 2 ending in e, I can append an e to it to get the string of size n minus 1 ending in e, right? Similarly, if I have a string of size n minus 2 which ends in a, then I can append an e to it and again get a string of size n minus 1 ending in e. And both of these scenarios will not breach the rule and will adhere to the constraints being given, right? Similarly, if I have to construct a string of size n minus 1 ending in I, then it will be equal to f of n minus 2, f of n minus 2 ending in a plus f of n minus 2 e plus f of n minus 2 I. Because here again what I'm doing is I'm just appending an I character after these strings and these strings to get the string of size n minus 1 ending in I. So what we can say otherwise about this notation is that current state, for evaluating current state for I is current state of I. For evaluating current state of I just need to append some characters and I'll get the current state from the previous state, right? So these are all the previous states. N minus 2 are all the previous states that we have evaluated, that we already have pre-evaluated with us, and using that we are evaluating the current states. Right? So if I were to denote this in the form of an array, if I try to denote this in the form of array, what I would do is I'm using a dummy place 0 over here so that this evaluation becomes easy. I'll be using these characters. Now initially for n equal to 0, I would say, no, for n equal to 1, first state, I can say all characters are equal to 1, right? These are the number of strings that end in a. This is ending positions. These are ending characters and counts of these basically, and this will denote the count for each ending position. So in this, what I'm trying to denote is for n equal to 1, this is the state I have. This is the state array that I have maintained. Now if I have to calculate the state n equal to 2, which is the next state, Now what can I do? If you look at this very closely, you'll notice that previous state of A, if I know, like over here I calculated the state diagram for A, for characters ending in A, the previous state of A is equal to the current state of A, or I can say current state of A is same as the previous state of A, right? Because we can only append a single character to it, A, which is A in itself. Then this n minus 2 A is nothing but n minus 1 A. That's what we just determined, right? So what we can say that if I know the current state of A, this is the current state of A, and I add it to the previous state of E, this is the previous state, and I add it to the previous state of E, then I will get the current state of E. Then I'll get the current state of E, right? And I can apply then this same equation I can just use over here also, that I can say that n minus 2A plus n minus 2E is nothing but n minus 1 E, right? Which is what? Current state of E. Current state of E. So if I know the current state of E and add to it the previous state of I, then I will get the current state of I, right? So by this expression, by this mode of expression, if I try to extend this array further, this is what I would get. I copy 0 as it is. Now previous state of A is equal to current state of A, or I can say, sorry, otherwise current state of A is equal to previous state of A. So this number gets copied as it is. Now current state of E is what I have to determine. Current state of E is what I have to determine. So what would it be? It would be previous state of A, current state of A plus previous state of E, as we have in this expression, which is current state of A, because n minus 2A is same as n minus 1A. So n minus 2A can be called as n minus 1A. Hence we can say that it is current state of A. We can say that current state of A. So current state of A, if I add to the previous state of E, then I'll get current state of E, which is 2. Now on the same lines of logic, we have this expression, which is nothing but current state of E, as we just determined current state of E. So current state of E is 2. If I add to it the previous state of I, then I will get current state of I, which is 3. And so on. I can apply the same if we extend these equations further for O and U, and like these other vowels also, we'll get the same rule. So I can add 3 to 1, I'll get the answer 4, and 4 to 1, I'll get an answer 5. Now if I have to get the total count for all the strings that end in 2, I need to add them up, sigma ARR I basically, and this will be equal to 15, which matches the problem statement being given. For n equal to 2, we have the answer as 15, right? And similarly, if I have to extend it further for the rule n equal to 3, then this is what I can do. For each state, 0 gets copied as it is. I'll just explain in a while why are we copying it. This makes the state calculation a bit easier. Now first state gets copied as it is. Now we add to this the previous state of E to the current state of A, so we get an answer 3. Then previous state, now this becomes the current state of E being added to the previous state of I. This becomes 6, then 6 plus 4 10, and 10 plus 5 15. So this would be equal to what? 25 plus 10, which is equal to 35. So this would be equal to 35, right? Now let's go through the code. Let's try and understand code a bit. So now let's try to understand the code part of this problem. So what we are doing over here is, this is the first state that we are beginning with, n equal to 1 is the first state for us. This is the array that we have taken, that same as we took in our example over here, right? Now in this array, after having been created this array, now what we are doing is we'll start iterating for each state. N equal to 1 is the first state, so this expression will go and hit n equal to 1. We are giving an expression less than or equal to 1, so we don't basically evaluate anything when I is equal to 1, because n is also equal to 1. And in that case, we simply go about summing all these for all the indices that we have just evaluated. So indices in our case are nothing but vowel ending character. So in this case, on adding all of these, we get the answer 5 for the very first n equal to 1 case. Then what will happen is, then we go to we proceed to next state, which is n equal to 2. So for n equal to 2 state, what we are doing is we are doing dp k. What is this dp k? This is the previous state. This is the previous state, and to this we are adding the previous character state. So as you can see over here, this is k minus 1. What is this? This is k minus 1, and we are adding it to the current value k while evaluating this current k, and we add to this to get the new state for k. We add this to get the new state for k. So this way we are adding it in a sequential manner, one after the other. So if I am on a given k, suppose over here I am, this is nothing but dpk. What I'll be doing is I'll be taking the previous value of the previous character. Now what is this? This becomes the current state for the previous character, and to this I will add the older value of dpk to get the new value of dpk. So this way, when I do this procedure repeatedly, this is the same expression that I'm trying to observe, and at the end we need to do the summation of this, because we'll be landing at the final state. As in this case, this state is nothing but count for individual characters, ending characters, and when we sum them up, we get this as an answer. So then we'll finally sum it up and we will return the answer as sum.